everybody. I hope everyone's having a wonderful day. So let's get started. So remember last day I introduced you to the dictionary. So remember, a dictionary is a set of records, or what we call records or items, each with a key, each with a value or data. So there's a pair. Key, data. Okay, so remember D has the following operations where D is a dictionary. So first remember, if you give it a key, it returns back the record's data given that key. So if it exists, it will give you back the data of that corresponding record. If it doesn't exist, just simply return null. I give you a key, some value or data, and I create a record. I put her into D. So I just make that, I have that record, I put it into D. Now, if it already exists, because remember, a dictionary is not allowed to have duplicate records in it. If it does have a duplicate record, meaning I've attempted to put in another record that is of the same key. Remember, the keys matter, not the data, the keys. If the keys are the same, when I attempt to put it in, I should return an error. So there's only a unique set of keys in my dictionary. So remember, kind of think of it like a phone book. Each record has a unique phone number. However, you might have more than one person with the same name. Okay? Likewise, I have remove, so I give you a key. I want you to remove the record with that corresponding key. Now, if it doesn't exist, just simply return an error. So you're going to return that value of that record if it indeed exists. Now, I mentioned that there's some other operations. So there's also size, so it returns the number of records in D. Remember, it returns the records, not just like if there's like multiple nodes in there, we don't worry about that. We care about the number of records. Is empty just returns false if there's at least one element, true if there's no records. Now, there's some other optional ones that I'll mention here. It involves around something called an iterable collection. So this means I have some way of going through the collection one after the other, using a so-called iterator. Now, an iterator just simply has a iterator method which returns back you an iterator object. So this object, so my collection will have an iterator method. It gives you back an object that is of type iterator in Java. And what it does is it just simply does the following things. So first, it has a next method, so if I use the iterator and I apply next to it, it just gives me the next element in the collection. And then it has this other one called hasNext, which just returns true if you're done traversing through all the elements of the collection. The way I analogize this is with a zipper. Now imagine you have your jacket zipped up, and you're zipping down the jacket. So the way you want to imagine this is when I get the iterator, I start off with my jacket fully zipped up. And the way it works is every time I apply next, I zip it one notch down the zipper. And I can ask the question, am I done yet? Which is hasNext. If I'm not done zipping down my jacket, I'll just say false. No, I'm not done. I might go down, all the way down until I'm unzip my jacket. And if it is the case that I've done unzipping my jacket, hasNext would be true. This will just keep giving back something like a null. So you might naturally think about, okay, well, Dan, what does that exactly mean? Imagine I give you something like a linked list. An iterator for a linked list would be quite simple. Each time you give me next, it gives me the data of the node every single time. So every time I apply next, it gives me one element, and then it proceeds to kind of, imagine just like my zipper, zipping down one notch, it gives me the next element. So it keeps giving me the next element and notching over one every time I apply next. Iterators aren't too bad. In the notes, I've supplied a link. If you check it out, it gives you a nice tutorial on iterators. So sometimes people will implement 3 different kinds of iterators. The first one is called entry set. That one gives you an iterable collection that gives you all the records. So no matter what the structure is underlying it, it'll have this iterator will give you back this behavior. And you can go through each one of the records one after the other, just like if you're traversing through it, but it's done in a very abstract way. I don't know what's going on underneath, what the data structure is actually doing. Those are things you would implement. There's key set. Again, same idea, except it goes through all the keys. and values just go through all the values. It's nothing too complicated. Okay? So that's what the dictionary is. So the main three here are the ones on the right here. Those are the ones we're going to focus on a lot when we talk about dictionaries. These other two, they're rather straightforward methods as long as you just keep track of the counts. It's pretty easy. Just to help emphasize the fact, remember, this is ADT. Now, what I want to do is I want to apply some operations to my dictionary. So imagine I started off with an empty dictionary. And what I'm going to do is I'm going to apply a series of operations. So imagine I give you some dictionary D. And something like Java, this would be like D dot is empty. And I would get back something. So, for example, if I start off with an empty dictionary, what should be the output if I apply is empty to D? What should it be? If it's empty, that means I should return back true, right? I should return back true because there are no records in my dictionary. It's empty, right? How about if I put the record with key 5 and value A into my dictionary? What should it do? Well, first, it's not returning anything right now, so it's not applicable. And then what it does is it puts that record into the dictionary. So now my dictionary has this key value pair. So now 5A is in the dictionary, right? Pretty straightforward. Same idea with putting 9 and B into the dictionary. So 5 and A. I can then put 9 and B. Now remember, it's the keys that have to be unique. So keep that in mind. Okay, how about when I put in 3, comma C? Okay, so far, 9B, and then I have 3C. So that one's not too bad. Okay, how about this one, the 7D? I think we're okay, right? I'm just putting more elements into my dictionary, some more records. So I have 5A, 9B, 3C, and now I have 7D in here. Okay. How about 3E? I want you to think about this. Okay, if I put in 3, comma E, what's going to happen? Remember what put does. Remember, we are caring about the ADT, not what's underlying it. So what happens with my dictionary if I attempt to put in this record with 3, comma E? What should happen? Well, first we need to make sure there's no duplicates, right? Okay. Are there any records with key 3 in there? The answer is yes. So I should report back probably what the data of that key was exactly. Well, it was C here, right? 3. So I get an error when I do this. Now, the convention we're going to stick by, at least in this course, is that when you attempt to put a duplicate record into the dictionary, it doesn't overwrite the old one. Can you think about why that might be a good idea? I'll let you think about that. One way you could view this is, okay, I am attempting to put something that already exists in here and try to overwrite it. Some would allow that to happen. That sometimes makes sense for your application. Other times it might be, hey, look, somebody's trying to put something into my dictionary. I don't want them to change my dictionary. So there's kind of 2 different ways you can look at this. So our convention is just going to be that it never overwrites it unless otherwise stated. Okay, how about this? Okay, if I attempt to get 9, what happens when I get 9? Well, it should be give me back. Okay, well, which record has key 9? This one. It has the data, which is B, right? Its value is B. So I should return back B. Remember, I'm just writing down what each one of the records is. Remember, nothing magical happened in between my steps. The dictionary just all of a sudden didn't fall off the face of the earth. Okay, how about when I get 2? What happens when I get 2? Okay, is there any record with key 2 in there? No, right? So it better return back no. So the dictionary hasn't changed. Okay, how about if I get 5? If I get 5, I should get back A, right? Dictionary didn't change. Okay, how about the size? If I get the size, how big is my dictionary? It's the number of records, right? How many records are there? Are there 3? Are there 3? Are there 2? Are there 5? No. There's only 4, right? 1, 2, 3, 4. That's it. Should be quite simple. So just 4. 5A, 9B, 3C, 7D. Okay. Let's go through some more. Let's go through some more here. I prepared in advance some more examples. So don't worry about what's on the left quite yet. We're going to get there. Okay, how about if I perform some remove operations? Okay, if I attempt to remove with key 5, what should happen? I want you to think about it. If I remove 5, so it's right here, right? I'm supposed to return what? The whole record or just its value or data? It's just its value, right? So I just want to I should get A back, right? Because that's the one with 5 in it. And I removed it successfully. So I have 9B, 3C, and 7D, right? I'm down 1. How about if I remove 3? What should happen? It should give me back C. And now I should have only 2 records in my dictionary. Just 9B and 7. So my keys are 9 and 7 here. Their respective data are B and D, or respective values. I will get 3. What should get 3 do? Well, I removed the record with key 3 in it, right? So it better return back null. How about is empty? Is it empty? No. No, remember, it's got 2 records in it. Right? That's not too bad. So I want you to remember, when we're talking about ADTs like this, sometimes we have to really think about what the operations are telling us, not what's happening underneath the hood. So notice that I applied these concepts without ever having to tell you how to implement them. So you see what I mean? That's what the power of the ADT is. It's both an abstraction, but also operates almost like a conceptual understanding or idea of what the data structure is, so that I can apply it in many different ways, kind of like a pattern out there. So I can kind of okay, well, there's so many things that look like dictionaries out there, I can easily apply the ADT to them without ever knowing how to actually implement it. So now that you get what a dictionary is, hopefully, if not, more than happy to answer some questions for you. Let's talk about implementing them. Let's build some data structures, okay? Let's think about some simple implementations for a dictionary. So, remember, I'm going to care mostly about get, put, and remove. I want you to think about how you could do that. So, one idea, this is a very simple way of doing it. Think about using something like an unsorted list, in particular using a linked list. So here's one idea for doing this. So I imagine I have a head for my linked list. And what it does is it maintains a link. So I just have a linked list that consists of all the records of my dictionary, right? So each one of these is its data or value. So these things are together, so I have my whole record as an object. It's within the node, and then has a next reference, okay? So these are my records. So each one of these, each data entry or attribute of the node is a record with a key, has the data, and it has an X reference, just like a linked list that we talked about before. So it's nothing too scary here. You might naturally ask, okay, well, how do I actually implement these operations then? I'll let you think about that. So remember, there's two things you need to keep in mind when we're doing this. One, the dictionary has to maintain unique keys. And I need to make sure I maintain them such that I can perform all these operations, okay? Let's talk about put first. So what would you do for a put? Okay, I have my linked list here. How would I put things into my linked list for my dictionary operation? Well, let's think about it. I need to make sure I'm not going to create a duplicate record, right? So I need to traverse this list to make sure that the current key value pair that I have, its key is not one that already exists in the dictionary. So I need to traverse this to the linked list, and then I can just simply insert, right? So just traverse the list, check for duplicates. For duplicates, return error if duplicate is found. So if you find a duplicate, you're gonna throw an error at the user. So you're just going to say, hey, look, it's something like Java, you throw an exception here. So you go throw, so you go no, you throw a new exception here. I won't get too much into the Java-isms of this. Just because, remember, the algorithms aren't supposed to be language specific too much. But anyways, so when I'm done doing this, what do I do? So just create a node, and insert it at the front of the linked list. Otherwise. So that's the idea of put. I just simply traverse through the linked list, so I just follow along. I assign like some reference to a node, cur, and I just simply go using a while loop, and I just simply check each one of these just to make sure I check the key to make sure that it doesn't duplicate the one that I'm going to be trying to put in. And if I run into no duplicates, I create a node with the record as its data, and then I just simply insert it at the front of the linked list, right? Pretty straightforward. Okay, how about let's consider some more operations. So put's pretty straightforward, right? How about get? I'll let you think about that. Okay, what would you need to do to get the record with a given, get the data of a record with a given key K? What would you need to do? Quite simple. Just traverse the linked list. If a node contains a record with key K, return its value. If the entire list is traversed, return null. If not found, right? That seems quite natural, right? All I do is I just go through each one of the nodes, start up here, go one by one until I find it. How about remove? It's not going to be really that much different, right? I just need to find it, right? And if I can't find it, I better give back what? I need to give back an error if I can't locate that record with that key, okay? So I'm just going to again reverse the list, and remove the node with the key K if found, and return its value. If the key is not found after examining each node, report error. Right, because I didn't find it. See, it's really not that bad. See, a linked list is a very simple way of implementing a dictionary. Now, let's talk about what exactly the time complexities for this will look like. So just keep in mind that I've written these in words. Now, because I don't really show a whole lot of Java code, I thought this would be a great opportunity to show you some actual Java code. So in the notes, I've actually included Java code for this implementation of a dictionary so that you can actually see some features of Java ranging from generic typing to how you can create a linked list in Java. So note that you probably will have seen and done it by the point you actually see this video probably. But the point is that there's some code. You can take a look at it if you like. If you don't like it, you don't have to look at it. I give you a whole bunch of complete set of code there, just so if you want to try it out. Or if you just want to see just for your own review. For example, I use some exceptions and some other things there as well. Okay, let's talk about the efficiency for this. So involving the worst case time complexity of each operation. Okay, so we're going to talk about the worst case time complexity. Now, fortunately, these are rather straightforward. So let's talk about them. Now, keep in mind when you're doing your homework, don't just assume that it's straightforward, therefore you don't have to write a whole lot. You need to justify things, just like we did in the past. Just for the purpose of time, because you've already seen what a linked list does. So what does put do? So put has to traverse through the linked list to check for duplicates, then it just performs an insertion at the front. So what does it do? It takes big O of n time. It checks for duplicates, right? That's why. So it checks for duplicates. That's really why it takes linear time. Remember, you have to check for those duplicates. Otherwise, you could introduce another duplicate record in, violating the properties of a dictionary. Okay? That's why you need that. That's why otherwise you could just say, oh, it takes constant time, big old one. So how about get and remove? Now, fortunately, get and remove are pretty similar. So we'll talk about get and remove at the same time. So what about get and remove? I want you to think about it. So if I want to go through this, remember each time I have to go through the linked list, in the worst case I have to traverse through the entire linked list. So it's quite simple. So, and when does that happen, by the way? Remember, you got to think about a worst case scenario. When does that happen? It happens when we don't find the record with that associated key, right? That means I have to go through all of them. So it takes big O of N time. When a record is not found, the entire list is traversed. Right, pretty straightforward. So that, believe it or not, that's one way of implementing a dictionary. It's pretty straightforward, right? I'm going to ask you a question, because you probably have been thinking about this. So how about if all the keys stay sorted? In the linked list. Okay, remember I just said, okay, I'm going to use an unordered list, right? I'm just going to make a linked list. I'm not going to care about what order the keys are in. Can I do any better if I were to maintain the linked list such that I keep all the keys in sorted order? Because remember, all of these operations, I can easily modify these algorithms so that I can maintain such a thing. It's quite simple. Remember the put operation, I always just insert at the front. All I have to do is I just need to put it into the appropriate spot, insert it somewhere, whether it be the front, back, or in the middle, or somewhere around the middle. I don't know, somewhere in the linked list. If I perform an insertion, I can put it into the spot where it needs to be appropriately and just maintain this process the entire time. I can do that and still get the same time complexities I had before. So can we do any better? I want you to think about that. Can we? Okay, so the answer is actually no. So the answer in this case is no. How? Okay, imagine I give you given records in increasing order. So what if I give you the keys in increasing order? So every single time I give you another record, the key itself, the number that is, every single time I put one in is 1 or 2, possibly 3 times bigger, or just simply just 1 higher. So for example, I might put in a record with key 1, then key 2, then key 3, then key 4. What happens with the put operation if I do that? It has to still traverse through the entire list, right? So it'll still have to go from left to right. And you could make a very similar argument where if I gave them in decreasing order, if you started from the back to the front, if you had a linked list where you have both in the front and the back, you could always try to do something like that. But either way, you're going to still have to deal with linear time. So the answer is no, but can we still do better? Well, a linked list maybe it just isn't the ideal way of thinking about sorted records. I gave you an algorithm that you can actually use to perform searches a lot faster, right? So all these operations are still going to take big O of n in my linked list, regardless. So how about if I consider instead how about if in a sorted array? So instead of using a linked list, we use a sorted array. Can we do any better there? Okay, so putting still requires me to go through and check all of them, right? Just in case for any duplicates. So what I can do is, so if they're already sorted, I can, actually, let's start off with some of these operations. I'm going to create a little table. So I'm going to have get, a key. I'm going to have put with a key and a value. And I'm going to have remove. I want you to think about the best thing you could throw at with these type of data structures. So we're going to have a linked list column. And you're going to think about the worst case. So we have a linked list versus a sorted array. The linked list versus sorted array. When I do get operations, I'm getting a little slippery here. Okay, so if I do linked lists, remember all of these? We already know these are all big O of n. In the worst case, those are all big O of n. Okay, how about the sorted array? Get. What can you do with a sorted array with the get operation? I could use binary search, right? So I can take big O of log n, which is much better, right? Much better. Okay, how about put? Okay, you might be thinking, I'm clever. So what I could do is I can look for the duplicate. I can look for that duplicate using binary search. And I can try to find if that key already exists in the array. Which I can totally do, right? See, that sounds pretty smart, right? Yeah, no, I can just use binary search again. Just make sure I don't have a duplicate, right? However, that isn't going to get you too far, right? I can search for the key using binary search. Then I see, hey, look, I have a duplicate or I don't. If I have a duplicate, I report an error. Otherwise, I just put it in. Okay, where are you going to put it? So if I give you an array, and it has some length, like length m or something, and it's saying it's completely full, like there's m elements in my array. What do I need to do if I want to put in my record? I need to expand and resize the array. How long is that going to take? Well, usually we would just double the size of the array or increase it by some amount. Later on, we'll talk about how doubling an array actually is a pretty effective way of resizing an array. We'll talk about more of that later on in the course. So I'll put that idea in the back of your head. That doubling the size of an array is actually not that bad of an idea. If I have to do that, however, that requires me to copy all the elements down, right? So that's a worst case scenario. It's where I attempt to perform a put operation when the array is already full. So regardless if I try to look for the duplicate or not, I need to still anyway resize the array. It's going to take big O of n. You can make, by very similar arguments, that this is also going to be big O of n. Why? Well, I could attempt to remove it. Okay, so if I perform a search, then what happens is I attempt to remove it. Well, I'm going to run into a problem very quickly, right? I'll still have to make sure I shuffle around elements. Because as soon as I do that, I'm going to have to shuffle the elements to fill the spot that used to be occupied by that key, right? So if I get rid of that record, I still need to make sure that I'm able to perform binary search to find and remove it, right? Now, if you're okay with having some gaps in there, that isn't going to be very nice when it comes to binary search. So that's why we're going to need that linear time here. It's because I might have to perform a number of shuffles, kind of like insertion sort. I have to perform a very long shuffling of elements, sliding them over. So that's why we're taking linear time here. Otherwise, you're going to end up with a bunch of gaps in your array, or you might potentially have to reduce the length of the array if you want to deallocate some memory. So we can get this pretty good. So remember, I have to resize. So these ones I have to resize the array or shuffle elements. There's no escape from this, really, with this approach. So we're going to talk a little bit about how we could do better than this, at least on an expected level. So this is a dictionary, right? It's pretty straightforward. Can we do any better? So we're going to shift gears here and talk about a brand new topic. So we've talked about dictionaries here. We talked about a couple different ways of implementing a dictionary. Let's talk about a brand new topic, which is going to be one way we're going to deal with some of the problems with doing this. So because I'm going to point out that these data structures are effective and I'll say for small dictionaries. I'm going to show you a way that you can kind of get around this issue. Because remember, these operations are going to occur in the worst case, right? I want to have some way I can deal with that. So we're going to talk about hashing. So our brand new topic is hashing. So I've introduced you to a couple of ways you can implement a dictionary. So I'm going to say, can we improve the main dictionary operations? So I'm going to be mainly focusing on average case. However, you're going to notice that worst case is still going to come up, but you're going to find that this is going to be fairly practical at the same level. So, yes, we're going to use hash tables. So I want to introduce you to the idea of a hash table. I want you to introduce you to the idea by just considering the possibility that I could have some table, which is going to be, for all purposes at this stage, you can think of it like an array, which is the table. Now imagine I have a whole bunch of records. Say I have M records, or M slots. I'm going to oftentimes refer to them as slots or records or positions. And imagine I give you a whole bunch of keys. Sorry, key value pairs. So what are these going to represent? So imagine I gave you the following. So consider the set of all possible St. FX student IDs. Each with digits, or running off to the side, with digits, D sub 8, D7, D6, D1, D0. So it's going to have 9 digits. And what's going to happen is I'm going to have a bunch of records that I'm going to put into this table. Now, the whole big idea with hash tables is I'm going to expend some memory such that I'm going to insert records into this table. And I want you to think about it kind of like what we did with the array. However, you have to be a bit more particular here. So you'll see what I mean in a moment. So I'm going to assume that this table has size capital M, which is going to be at least the size of the number of elements that are going to be in the table. So you might naturally ask, okay, well, this seems like a lot of IDs. Well, what I'm going to do is I'm just going to imagine that I have a bunch of key value pairs. So K1, V1, K2, V2, K3, V3, and so on. And Kn, Vn. And what I'm going to do is I'm going to take each one of these keys, one after the other. When I want to put them into this table, I'm going to take advantage of something called a hash function. So what the hash function is going to do is it's going to take a key. So for each one of my put operations, for example, or get operations, or remove operations, I'm going to use this hash function to tell me where that record is located in the table. So it might pop up here, it might be there, it might be here, it might be there. So for example, say imagine K1 went right here with V1, K3 went here with V3 here, and then let's say Kn went here and with Vn, and we have K2 down here, K2, V2. Now you might naturally ask, okay, well, what's the purpose of the hash function? Now let me explain this. So let's talk about this. So imagine I have all the possible St. FX student IDs. Now, there's a bunch of these. Now, you really could not give me every single St. FX student ID that's possible, right? Student. Why? So each digit di has 10 possible values, right? What are those 10 possible values? So you got to think about each digit. Now, remember it's an ID, so 0 can be the first position. So there's 10 of them. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are your 10. How many digits do I have? 9 of these. So the total number of possible keys is what? What is it? Each one is 10, so I have 10 possibilities. Then I have another 10 possibilities. Then another 10 possibilities. And I do this 9 times. So how many possibilities can there be? There are 10 to the 9. That's a lot of keys. That's a lot of unique keys. So what's going to happen? Now, I typically am not going to want to store all my records, so every single one of the IDs in my table, unless I absolutely need to. You could think of all the possible student IDs as some sort of universe of keys that I could have. And I could put them in, I could remove them. But the whole idea is that I'm going to try to get it so that I can spread the records across the table such that when I look up using this hash function, that it gives me the position and I don't have to go scanning through the entire array or the entire table. So the whole idea here is that I'm going to have some key. I feed the key to this hash function, which, by the way, we typically want in practice to take constant time, so it should be fast. And what it does, it tells me a position. So it's almost like what? It's almost like what? When I go and use an array and I look up a position, how long does it take me to look up that one position given its location? So if I want to find, what's the 5th element in an array? Well, it's big O of 1, right? So I want to take advantage of the locality of a table. So instead of having to do this traversal business, because I want to stay away from doing that if I can, instead what I'm going to do is I'm going to have this hash function tell me where the record is. And then what it does is, okay, well, if that takes constant time, and to look in this position takes constant time, then the whole thing's going to take constant time. That's going to be our goal if we can. I don't want to spoil it quite yet. So I want you to think about this. Now, I told you that it's likely that we're not going to be able to put all of the records in our table such that everything's going to fit hunky-dory in this, right? Why? Because of the following fact. So imagine I give you a table. So imagine I have some records, some slots. Say it has 10,001 entries in it. More than sufficient for what we need it for in terms of this application. So just think of this as a really big array. So what's going to happen? Imagine I give you 2 records, one with an ID called ID1. The idea is that I feed the ID to this hash function, and it tells me, okay, well, where's it going to go? It's going to go right here. It says, hey, look, ID1 is going to go right here. However, there's a real possibility, depending on what this hash function looks like, that I can come along and give you another student ID, say ID2, and I feed it to the hash function, and it tells me it should go here. That is going to be a problem for us. This is what we would refer to as a collision. So collisions are going to occur. So remember, the big game plan is the following. I have a table. I'm going to attempt to enter records into the table by using this hash function. This hash function should be efficient. And what I do is I feed it the key and it tells me a position where to put it in the table. Now, the whole idea is to spread out the keys so that I don't get this collision to occur. Now, if I can achieve this on average, then I can get average case complexities of constant time, which is quite good in practice. So, the natural question is what we're going to do with these collisions and some other things. So, there's going to be some key design issues we're going to talk about. So, I'll talk about these design issues and then we'll wrap things up here. There's going to be these big issues when we talk about designing hash tables. So when considering hashing, one may consider the following. So there's going to be some of these things or things that we'll always have to take into account here. I'm going to hopefully address each one of these for you when we talk about hashing here. So determining the table size. So how big this table needs to be for us to take advantage of it such that we get nice results for our efficiency. So what does the size of the table need to be? Now, typically if you know how many things you're going to put into it, you need to make sure the table is at least that big. But what's the ideal size? So I'll say, what is the ideal, and I'll put ideal in quotation marks, ideal size for the table. So that's the first design thing we need to take into account when we do this. The next one is the selection of the hash function. So as I already told you, it should be efficient to compute. And I'll say ideally constant worst case. Time. So remember, the whole idea is I want to have a nice efficient hash function so that what happens is I give you the key, I hash it, I can put it into a position. Then I can also retrieve it, kind of like I was just accessing a position in a table or an array, which we know how to do that in constant time, right? So I want to take advantage of that fact, the locality of the memory, as opposed to this idea when we had the array where I had to do the scanning business, where I had to scan. I don't want to avoid doing things like that. Instead, I want to just get in there big bang, just try to locate it. And I want to, it causes few collisions. And it must spread keys uniformly across the entire table. And finally, the last one is collision resolution. Collision resolution. How to deal with the collisions. Because I need some way of dealing with those collisions. These are going to be our big problem point, are these collisions, how to deal with them. So these are going to be the big things we're going to look at in this next section of this course. We're going to talk about hashing. Remember the big picture idea. I have keys that for my dictionary that are part of records. I want to put them into the table, but I want to take advantage of the fact that I can try to insert them in near constant time on average if I can. But I need to avoid these collisions. Okay? So next day, we'll talk more about hashing and we'll address some more things. So thank you very much and have yourself a beautiful day.